so that camera can take 30-minute videos. It can take lots of 30-minute videos, but it can take 30-minute videos. So I've got my phone set to bling-a-ling-a-ling every 30 minutes, basically, so that I can not have the audience at home miss anything, so to speak. So that's why occasionally I'll be going like, oh, we're going to know fix the camera. Who wants to get started?
All right.
Okay, you volunteer.
Not ready. Okay, can you explain flux freezing?
Can I explain flux freezing? No,
Yeah.
turns out I can't.
Cool beans.
All right. Flux freezing, what's the deal?
It is in chapter 14.
Oh, I know.
Oh.
That was my generic to the crowd. Flux freezing, what's up with that? You know, that kind of thing. So, flux freezing is the idea that magnetic field lines in plasma move together. That's what it comes down to, is the sun is ionized, it's a plasma, it's a gas where many electrons have been stripped off of atoms, and so therefore it's electrically conducting, currents can flow in it. And in that circumstance, if you have magnetic field lines that are embedded within a plasma, then they move together, it turns out, because if they tried not to do that, electric currents would flow, which would generate magnetic fields, which made the total magnetic field be such that they move together. So that's really what it comes down to. If the plasma moves around, it drags the magnetic field lines with it. That's what flux freezing means. It's kind of a funny name. We say they're frozen in, even though they have nothing to do with temperature. That's what flux freezing
What
is.
happens if you don't have it?
If you didn't have it, you wouldn't have sunspots.
Okay, so it helps with the sunspots.
Yeah, it's responsible for the fact that there are sunspots, and in fact, also it plays a key role in the sun's magnetic cycle in general.
Okay.
In this room, you don't have flux freezing, because the gas in this room is not ionized. So if I have a magnet in this room, and I go, then the air just blows right by the field lines, and they're like, yeah, whatever. However, if this were a plasma, and I went, then that wind of plasma would take the magnetic field lines with it, is what happens.
So you wouldn't have like the 11-year cycle and the 20-year
Wouldn't have any of that. The sun would not be magnetic if it weren't for flux freezing.
Okay.
Yeah, so the flux freezing makes sunspots because in the sunspots the magnetic field is really strong, so we get this additional factor called magnetic tension, where the magnetic field lines resist being bent. And inside sunspots, they resist being bent enough that in combination with flux freezing, it prevents convection. Because for convection to take place, not only do you have to go up and down, you got to go side to side. And in the sunspot, you got these strong magnetic field lines, which are saying, you're not going to bend us, you're not going to move us around. And so as a result, the plasma isn't able to go side to side. And therefore, that switches off convection inside the spot. And that's going to choke off the flow of energy from below, because convection is how the sun transports energy upwards in its outer layers.
Awesome. Thank you.
Any questions about that? Any follow-ups on that? All right, next question. Okay, if no one else is going to, yes, all right.
It says, be able to explain what provides the source of energy by which a protostar shines, but be able to explain what causes the transition from protostar to full-fledged star. Can you just go over that process?
Okay, so let's start with, excuse me, what's making the sun shine? Why is the sun shining?
Because of nuclear fusion.
Because of nuclear fusion in its core, right? Nuclear fusion in its core, and that requires the core to be hot enough in order for nuclear fusion to take place. Today, the sun's core is in fact hot enough for nuclear fusion to take place. But what about when the sun was a baby? It was much unlike human babies, which get bigger as they grow up. Star babies get smaller as they form, because you start with a big cloud of gas that slowly, for the sun, over about 30 million years or so, shrank down to form the star. Early on, was the core hot enough for fusion to happen?
No.
It was not. Early on, the core wasn't hot enough for fusion to happen, so it can't be fusion that powered baby protostar sun. Instead, it was shrinking, and whenever an astronomical object like that shrinks, it converts what kind of energy into what other kinds of energy?
Gravitational
It
potential.
converts gravitational potential energy into thermal energy and radiation. So in other words, a protostar, a baby star, isn't powered by fusion, it's powered by gravitational contraction. The conversion of gravitational potential energy into thermal energy and radiation as it shrinks. And so the core, along with the rest of the star, keeps getting hotter and hotter and hotter. And if it's big enough, if it has enough mass, more than about 8% the mass of the sun, eventually the core gets hot enough to light up fusion, and that's when a star is born. It's a protostar up to the point where the core reaches 10 million Kelvin and can then light up sustained hydrogen fusion into helium. That's when it becomes a star. That's that transition point. Yes?
During that process where it goes from protostar to star, by turning gravitational potential energy and thermal energy, it's able to release enough of the thermal energy off at a steady rate. So that way, it doesn't get hard on the side to stop gravity from.
Yeah, so as it's contracting, it's continuing to heat up, but the whole time, it's always true that the gravity is stronger than the pressure. In order to bring them into balance, you need the nuclear reactions. When the nuclear reactions start up, then the star becomes stable. Then you've got enough of a source of pressure in there to balance gravity. Until then, they're almost but not quite in equilibrium. Gravity is always a little bit stronger than pressure, and so it keeps on heating up. It never reaches the point. And even if it did somehow heat up at some moment to enough to balance gravity, it wouldn't last because it would keep giving off energy while no longer contracting. If it was no longer contracting, it wouldn't be making any more energy, and so it would give off the energy it had until it cooled down enough until it would start contracting. But in fact, that doesn't even happen. It always keeps contracting. Nice that I'll have a permanent video of you coughing. Okay. Yeah.
How long does it take for it to like start the nuclear fusion?
Depends on the star. So, like everything else, the more massive the star or protostar, the faster it goes through its life. So there's a figure in your book, which I think I included in here. Yeah, so here's protostellar evolutionary tracks for various masses. For this half solar mass star, 150 million years. For the sun, to about 30 million years. 3 solar masses, 3 million. 9 solar masses, 150,000. 15 solar masses, only 60,000 years. Because the more mass of the protostar, the stronger its gravity is, the more rapidly it collapses as a result of that. So like anything else, bigger stars, more massive stars do everything faster, including forming.
Thank you.
Yes?
Which energy is the one that makes the protostar shine?
The gravitational contraction. Yep. So gravitational contraction until it hits the main sequence. What makes it hit the main sequence is lighting up fusion in the inside. Because remember, what is it that makes a star on the main sequence? All main stars are doing what in order to get their energy? All main sequence stars, what's their source of energy? Nuclear fusion, potatoes into ketchup? What's fusing into what? Hydrogen into helium. Yep. Hydrogen into helium in the core is what powers main sequence stars. Yes?
I understand the conservation of angular momentum, like the description, but can you talk about the formula a little bit?
So the formula, right, so the L equals 2 pi times I times F business, right? So angular momentum conservation, I'll do it in a second. Move it down if I want to. So, angular momentum conservation formula says L, the angular momentum. So for whatever reason, L stands for angular momentum. I guess there's an L in angular, who knows? Equals 2 pi times I is the moment of inertia, times F is the rotation frequency, and remember that moment of inertia is a measure of how far mass is distributed from the axis of rotation. So if I'm spinning like this versus spinning like this, my moment of inertia is bigger when my mass is spread further from my axis of rotation. Meanwhile, rotation frequency is number of turns per unit time. So if for something like an ice skater, it could be rotations per second. For a protostar, they spin very, very slowly. The cloud spins very, very slowly. So the time, in terms of rotations per second, would be a very tiny number. Whatever you choose for your time limit, rotations per that time unit is the rotation frequency. And in the absence of external torques, what's true about the angular momentum? Does it increase, decrease, or stay the same? Stays constant. If there's no external torques, L, the angular momentum, stays constant. If there's no external torques, torques are what cause rotation. Like if I push on a door, I'm exerting a torque on it to make it rotate around its hinges. Roughly speaking, the torque is the force times how far I apply it from the axis of rotation. So constant if no external torque. And for a collapsing protostellar cloud, there isn't really anything to exert external torques on it. As the cloud collapses, what's happening to its moment of inertia? If the cloud is collapsing, what's happening to I, the measure of how far stuff is distributed from the axis of rotation? Getting smaller, right? Decreases as cloud, or stellar core for that matter, shrinks. So we've had a couple of applications of the idea of angular momentum conservation. One is when a protostar is forming. As the cloud collapses, its moment of inertia goes down. Two, when a massive star blows up good, when its iron core collapses, its moment of inertia rapidly decreases because it starts as a sort of iron white dwarf in the middle of the star, and how big are white dwarfs? About what's something that's about the size of a white dwarf? Earth. It collapses to form a neutron star, or maybe a black hole, but let's say a neutron star. How big is a neutron star? What's something that's about as big as a neutron star? A city. So it goes from the size of the Earth to the size of a city in a fraction of a second. Its moment of inertia decreases spectacularly when that happens. The angular momentum stays the same. So if 2 pi, which is hanging around as an observer, times I times F, so if moment of inertia times F stays constant, if I goes down, what has to happen to the rotation frequency?
Go up.
It has to go up to compensate. Goes up to compensate because L has to stay the same. And so that's why if a skater starts spinning with their arms spread out and brings in their arms, they start spinning a lot faster. I was faking it there, but if I were on ice, it would have happened. Or if I was sitting on a rotating chair with weights and I pulled the weights in, I would spin rapidly and almost kill myself falling off the chair, as I like to do. Similarly, a collapsing protostar spins faster as it rotates. One effect of that is flattening out into a disk, the protostellar disk surrounding the protostar. A neutron star spins so rapidly after it forms, again because of angular momentum conservation. The iron core collapsing spectacularly decreases the moment of inertia, so it spectacularly decreases the rate at which it's spinning, which is why we can get rapidly spinning neutron stars, and rapidly spinning neutron stars sending out beams of radiation produce what observable effect? Rapidly spinning neutron stars sending out beams of radiation are what we observe as pulsars. Pulsars. Yeah, pulsars. Is that okay? Okay. Any other questions about that? Or any of that stuff? All right. I'll get you soon, but yeah, let's okay, so yes.
Can you talk about stellar parallax and how can we use it to determine the distance to the star?
Yep, so stellar parallax is utilizing the fact that as Earth goes around the sun, our point of view shifts as a result of that. It's for parallax with just like your eyes, we did in class the idea of hold your thumb out in front of your face, blink your eyes. The line of sight of your two eyes to your thumb is different. Your left eye sees your thumb in front of other things than what your right eye sees your thumb in front of. The further away your thumb is from your eyes, the smaller the effect is, because the angle is smaller for greater distances of your thumb. Your brain, without you having to think about it, is constantly using parallax information to give you your depth perception when both eyes are open. Stars are way too far away for that. We need a bigger baseline. We need something that's a lot bigger than the distance between our eyes. To the rescue comes the fact that we are orbiting the sun. And so what we do is, if you observe a relatively nearby star, and again, I have to emphasize, stars are way, way, way farther away from us compared to our distance from the sun than this. Even the nearest stars is like 300,000 times further away from us than the sun is. So this is exaggerated for clarity. Here's Earth, say today, Earth 6 months later. The line of sight to star A shifts as a result of that. And so, in principle, we see star A in front of different stars 6 months from now than we would today. Same for star B, but the effect is smaller because star B is further away. Makes the shift smaller. This is greatly exaggerated, but in other words, the idea, here's the view today. Star A and star B appear to shift back and forth in front of the background stars. The closer the star, the more it shifts back and forth. Half the shift is called the parallax. Half the shift angle, the angle by which it shifts back and forth, half of that is called the parallax. So if I turn this measurement into an angle on the sky, half of it is the parallax angle for the star. They're never as big as this. Even the biggest parallaxes are all less than 1 arc second, 1/3600th of a degree. So they're always really, really tiny. But we can define things so that there's a nice convenient formula which says that the distance to the star is just 1 divided by its parallax, where d is in what unit? What do we call distances measured in terms of measuring parallaxes? So if the parallax is 1 arc second, the distance is a parallax second, or in other words, a parsec, d in parsecs. PC is the abbreviation for that. P, the parallax, is in arc seconds. So half the shift angle measured in arc seconds is what we can use to determine the distance in parsecs from that formula. So something which was something which had a parallax of 1 arc second by definition would be 1 parsec away. No star is as close as that. Even the closest star is like 1.2 parsecs away from us. Does that make sense? Or do you have more questions about that?
How do they influence one another?
You measure the parallax in order to determine the distance. In other words, you measure how much the star appears to shift back and forth to calculate the distance to the star. It's not that they influence one another, it's that the distance to the star is y the distance to the star is why it's showing a parallax. If we're closer to Earth, just like if your thumb is closer to your eyes, the star shifts back and forth more. If it's further away, it wouldn't shift back and forth as much. You could use a little trig to find out, you could measure the angle your thumb is shifting back and forth and use that to, if you knew how far apart your eyes were, you could use that to calculate how far away your thumb was. Your brain does that, as a matter of fact. So this is the relationship right there. That makes sense? Or, yeah? Any other questions about that? Okay, what's next? Yes?
You go over the Balmer thermometer.
Balmer thermometer, yes. So, the idea with the Balmer thermometer is that we can determine a star's temperature from the strengths of its spectral lines. So, let me do that here. I guess that would be 15 for the chapter. So the idea is that spectral lines of hydrogen are darkest, i.e. strongest, in stars with a temperature of around 10,000 Kelvin at their surfaces. They are weaker in stars that are hotter than that. They are weaker in stars that are cooler than that. So I like to think of it as the story of Goldilocks and the three stars. Goldilocks wants to find a star with nice, strong hydrogen lines because, I don't know, I guess she thinks they're pretty. And so, first Goldilocks goes to a cool star, a star whose temperature is much less than 10,000 Kelvin. Why is that star too cool? Because the Balmer lines of hydrogen are formed when, I gotta find the, I have it here somewhere. The Balmer lines of hydrogen are formed when, if we're looking for absorption lines, the electron is already in the n=2 level and jumps up to a higher energy level. So in other words, if it's in the ground state, that's no good because that produces Lyman series lines. So you need the atom's electron, the hydrogen atom's electron, to already be in the n=2 level. And the way that electrons get to the n=2 level out of the ground state, one way is to absorb photons, but even more so, collisions with other electrons, with atoms and so forth, can give electrons energy to jump up to the n=2 level from the ground state. In a cool star, not enough collisions are energetic to kick electrons up to the n=2 state, and so virtually all of the hydrogen atoms have the electrons sitting in the n=1 state, the ground state, where they can't make Balmer lines. If the star is too hot, the collisions are so energetic that there ain't no electron. It gets completely stripped off of the atoms. If there's no electrons around the hydrogen atom, you couldn't get any Balmer series absorption lines. 10,000 Kelvin is the ideal compromise, where the collisions are frequent enough and energetic enough to get, it's still a small number, but the optimum, the largest possible number of atoms having their electron in the n=2 level, ready to absorb photons in the Balmer series of spectral lines, but not so hot that you end up stripping most of the electrons off from the atoms. And so, from the strengths of the Balmer lines, we can infer what the temperature is along this scale. In other words, the further away you are from 10,000 Kelvin on either side, the weaker the spectral lines become because you're moving away from that ideal condition of optimal for getting as many electrons excited in n=2 as possible, ready to absorb Balmer series photons without having them be ionized, without having them be stripped off. Questions about that?
Wait, so which one is the brightest emission lines?
No, not emission lines, they're absorption lines. So they're not bright, they're dark. Right? So
Okay.
stellar spectra are absorption line spectra, a rainbow with dark lines in front of it.
Right.
10,000 Kelvin is about the ideal temperature for making the strongest Balmer series absorption lines. Here's Here's a whole series of stellar spectra, and you can see that it's actually closer to like, it's like 9,500, something like that, but I just rounding off to 10,000. A0 is the spectral type corresponding to the darkest hydrogen absorption line. So this is the same hydrogen absorption line in all these spectra. Notice it's broadest, it's darkest in the A0 star. That's the one that has that ideal temperature for getting as dark a spectral line as possible. It has the largest fraction of hydrogen atoms sitting in N equals 2, ready to absorb Balmer series photons. Any hotter than that, and you get more and more of the atoms ionized, and they can't contribute. Any cooler than that, and you have a greater fraction of them sitting in the ground state instead of in N equals 2. That's the ideal situation, is close to 10,000. Other questions about that? Follow up on that. Okay, you've been waiting.
Yes, so the hydrogen 2 region.
H2, we just say H2.
Mhm. So I know that it loses an electron. That's, is that how it's ionized, or?
No, in an H2 region, the reason that they're ionized is because of ultraviolet light from the surfaces of hot young stars inside of them. So O and B type stars giving off ultraviolet photons. If the star is hot enough, then most of the photons from them or a lot of the photons from them are more than 13.6 electron volts in energy, so that if they encounter a hydrogen atom, even one with the electron sitting in the ground state, it can strip the electron off of it. And so in an H2 region, what happens is that the electrons are stripped off of many of the hydrogen atoms. At the same time, free electrons can recombine with protons that earlier had an electron stripped off of it. And when the electron recombines with the proton, it's generally captured into an outer orbital, and then it starts dropping down towards the ground state because it, quote unquote, wants to be in the lowest possible energy, not literally, but that's the way it works out. And as it drops through the energy level tree, on the way down, it emits spectral lines, wavelengths. And so, in particular, hydrogen atoms in an H2 region where electrons are dropping down to the N equals 2 level before they drop down to the ground state produce Balmer series of spectral lines, and those blend to form a pinkish color to the human eye, which is why the H2 regions are pinkish in color. That's the next chapter for a picture of it. But that's what's going on there. So that's recombination radiation is what's causing the H2 region to glow like that.
Is it ultraviolet light?
Ultraviolet light from hot O and B type stars that are formed, because H2 regions are stellar nurseries. They're regions where stars are being born. The stars which form fastest are the most massive ones, the O and B type stars. O and B type stars are hot, and so they're giving off a lot of ultraviolet light. And that ultraviolet light, that would be my phone saying, oh, time to restart, okay? That ultraviolet light, I didn't even know the alarm sounded like that. I haven't used that particular one before. It's a countdown timer. Anyway, that's what's going on there.